We'll now move on to a section that deals with kinetic molecular theory of gases. And in this video, we'll introduce average kinetic energy and talk about distributions of speeds. Kinetic molecular theory is all about studying the motion of molecules in the gas phase. So let's consider a balloon that's filled with a gas. We want to answer a few questions about these gas particles that are in the balloon. We want to know what speeds the molecules or atoms are traveling at. We want to know how they move. Are they moving in straight lines, or are they moving in curved paths, or in some other way? And we're also interested in knowing how many collisions there are between gas particles, because collisions are necessary in order for chemical reactions to occur. And so it's beneficial for us to think about how many collisions occur, because the more collisions you have, the higher the likelihood that you might have a chemical reaction. We'll first talk about average kinetic energy. Now, the book goes through a derivation that shows where this equation comes from that allows you to calculate the average kinetic energy. And I'm not going to test you on the derivation for this, and so I'm not going to go through the whole proof here. But if you want to see it, I'll refer you to the textbook that goes by a step-by-step proof of the following equation that says the average kinetic energy of an ideal gas is equal to 3/2 times the gas constant R times the temperature. Now, in this equation, if you were to calculate energy, you'd want to make sure that you use the value of R that carries units of joules per mole per Kelvin, because we typically express energies in units of joules, and so you want to use the R that has joules in it. That's the 8.314 value. Let's take a look at an example here. We have 4 identical 1-liter flasks, each containing 1 mole of a different gas at 25 degrees Celsius and 1 atmosphere. And I want you to determine in which of these samples the gas will have the smallest average kinetic energy. Would it be in the helium, the methane, the chlorine, or the NH3, or do all the gas samples have the same kinetic energy? Take a moment to think this over, and then we'll go over the answer on the other side of the question. Alright, in order to make predictions, it's helpful to take a look at equations and see what variables will affect the kinetic energy and what variables do not affect the kinetic energy. Our equation for average kinetic energy that we just saw on the last slide was average kinetic energy equals 3/2 RT. For an ideal gas, average kinetic energy is a function of T only. It does not matter what the molar mass is. It doesn't matter what anything else about it is. It's a function of T only. Now, we can see in this equation that there is a direct proportionality between temperature and average kinetic energy. If you were to increase the temperature, then you would increase the average kinetic energy of the gas, but that's the only way that you could change the average kinetic energy of the gas. In this problem, all the gases are at the same temperature of 25 degrees C, and so all of the gases will have the same kinetic energy. Therefore, the answer here is E. All the gas samples will have the same average kinetic energy because all of the gas samples are at the same. Let's now talk about molecular motion. First of all, it's important to note that molecules will move at different speeds in the gas phase. So let's say that you have a sample of oxygen gas. The oxygen molecules are all going to be traveling at different speeds. They're not all moving at a uniform, constant, same speed. Additionally, molecules are going to move in straight lines between collisions, assuming that you have ideal gas behavior, no interactions between the molecules. And so that's what this figure here shows, is the motion of this particle. It's going to travel in straight lines in between collisions. The only thing that's going to change the trajectory is when it collides with either the wall, like it does here, or if it were to collide with another gas particle. And that would allow you to change the direction that the particle is moving in, but it's always going to travel in straight lines from one collision to the next. Lastly, the molecules are on a random walk. They're traveling randomly around in the gas phase, and again, moving in straight lines from one collision to the next. Let's now talk in more detail about the distribution of speeds for gas particles. Before we get into that, it's helpful to think of other examples where we see distributions. Another place where we might see that is maybe if we were to think about how not every single person in this class is the same height, right? There's a distribution of heights. You're not going to have every person, 5 feet 9 inches tall. There's going to be a range. And in this range, there will be, some people who are shorter and some people who are taller. And at one extreme end of the distribution, you'll have a very small number of people who are very short. And at the other extreme end, you'll have a very small number of people who are very tall. And then there's a sort of a bell curve that you can make that plots out how the number of people with a given height varies. Similar sort of thing applies here when we're talking about distributions of speeds. So we're going to take a look at the speed distribution for oxygen molecules at standard temperature and pressure. And it would look a little bit something like this. What we're plotting out here is the number of oxygen molecules that have a given velocity. And very few molecules have very low velocities around 0, and very few molecules have high velocities around 1,000 meters per second, let's say. And then we have this whole range in between. And what we recognize here is that it does adopt a similar sort of a bell curve to what you would have if you were to plot out, let's say, a distribution of heights, right? So the important takeaway message here is not every molecule travels at the exact same speed, and we do get a distribution. Some molecules travel faster than others, and you can see in this speed distribution that there are some speeds that are more popular than others, right? Like there are more molecules traveling at 400 meters per second than there are at, let's say, 800 meters per second. But not every molecule travels at 400 meters per second. You do have this range of possibilities that exists here. That brings us to the end of this first video. And in our next video, we'll talk about how you can calculate average speeds based on the speed distribution.